welcome everyone to this tutorial on nucleation modeling in condensed matter, materials in general. I hope you might have seen the videos that I've posted. There are 70 minutes of stuff, of material, where I go through quite a lot of aspects of this field of nucleation theory. I wonder if those who are happy to do so would turn on their cameras, just to give me a quick idea of who's here.
Must be nice to see people. I'll do this.
Hi. It's nice to see faces rather than icons and stuff. Well, it's good to have a bit of contact in these funny old days. As I said in one of my lectures, it's a bit weird to be talking to a webcam instead of real people, so it's always valuable to do so. And by the way, you don't have to keep your cameras on if you prefer not to. I'm not forcing anyone to do anything, but it's nice to make your acquaintance. Okay, you may or may not have seen all those videos. That's a shame if you did not, because it will be hard for you to follow perhaps what I'm going to be covering this afternoon. Or perhaps I should say what you will be covering, because my aim in this tutorial is for you to ask me questions rather than for me to guess what questions you might have for me, and for me to attempt to clarify them here on the whiteboard. Nucleation theory, I gave you 18 pages of stuff. It's actually lifted out of a lecture course that I do at master's level. So it's rather more detailed than perhaps you're used to in this series, but I thought I would give you more rather than less material. But I hope from the 3 lecture videos that I supplied to you, that you've got at least some gist of what all this is about. This is about the way phases change, the way materials change their phase, and what is difficult about the modeling of that process. That's the theme I was trying to sketch in those videos. What are the factors that control the rate of formation of a new phase? Now I'm looking out of my window and I can see a new phase forming as we speak. Namely, I can see water droplets, a mist outside. It's a misty, damp, drizzly, nasty sort of day, at least it is here. And there's a phase transition going on out there where the water vapor, the gas phase, is condensing into little droplets, making our lives miserable. And I can tell you that the modeling of the formation rate of droplets out of a humid atmosphere is a really difficult problem. It's one that has engaged me for most of my research career because it requires us to do quite a lot of statistical physics at the molecular scale using tools that have not always been well understood or well established. But nevertheless, and still to this day, do not provide us with exact predictive power on how wet we will be if we go out in a humid atmosphere at a certain temperature and the mist starts to form around us. The question is, are these mist droplets going to be few in number but rather large, or are they going to be rather small but very numerous? This is all about what is the rate at which a new phase forms out of an old metastable phase. I gave you a lot of material on that, and I gave you ideas of arising out of thermodynamics and out of kinetics. There was an initial concentration on the thermodynamics of phase change, coexistence and change. And then the latter part of the lectures was all about the kinetics of change, how one speaks about probabilities changing as time progresses, such that you go from the vapor phase the gas phase into the liquid phase. So I gave you lots of material. As I said at the beginning, I'm hoping that this is a session where you ask me questions, as well as I go on and on. But what I don't want to do is just monologue for 50 minutes instead of listening to you or having you discuss things amongst yourselves. In fact, that's the first thing I'm going to do, is I'm going to send you off into breakout rooms, assuming I can now open them. I was told I was going to be able to open breakout rooms as the host. Am I host? I'm the co-host. Excuse me while I...
I'm going to make you host now.
Oh, okay, you're still here, Karen. I thought you'd gone. Okay.
Oh, right.
If not, then perhaps if you can open up breakout rooms.
You should be host now.
Okay. Okay, so I am. That's good. And I can see breakout rooms. Okay, let me give you a task. I'm going to send you off into breakout rooms. There's 14 people here, including myself, 13. So I'm going to send you out in perhaps groups of 3. And I want you to take a look at the following questions, which I'm going to share with you shortly. Share screen. Okay, I hope you can see 10 questions. And you're going to go out into rooms with a number attached to them. And I want room N to address question N. You don't know yet which room you're going to go into, but it'll become clear. And when you're there, you can pop back to this main screen in order to remember to check which question it is that I want you to look at. So there's quite a few here, but and if we have 3 groups, maybe we'll revisit them at least twice. And then we'll come back together and I will receive questions from you, and then I shall address them, or other people will perhaps. Okay. So I'm going to unshare and send you out into 3 breakout rooms where I'd like you to talk to each other and address one of these questions. As I say, you can pop back into the main screen where I'll share the screen once again, and you can find out what the question is. I'll give you 5 minutes in these rooms. Okay, I'm sending you out now. Okay, you should all be back. So here are the questions that you were addressing. And I'm going to be very cruel now and ask somebody from group 1, room 1, to tell me what is the grand canonical ensemble. Who's going to tell me?
Okay, so, oh, sorry. We were saying it's just a way of describing a system where you have a constant chemical potential, volume and temperature.
Yep. Particle exchange, heat exchange, constancy of volume, system, and environment or bath. Okay, and then you have probabilities which go like an exponential of energy minus mu n, where energy and n are system parameters, given the temperature T, which is an environmental parameter. And that's the statistical mechanics that we are using in nucleation theory, because we're interested in particles accumulating, changing a phase from one form, maybe a rarefied gas, into a dense form, maybe a liquid. That's all there is to say, really, except it's an equilibrium ensemble. Okay, here's a comment to give you. These are equilibrium probabilities for certain structures forming within the system. And at first sight, it doesn't seem that this is going to tell us much about a non-equilibrium process, namely of nucleation, which is a time-dependent non-equilibrium change of state. All right. What about room 2? What is the availability potential? Anyone? Somebody?
Would it be something where it's a more elaborate model which can model these simple fluids in terms of understanding these phase coexistence?
Yeah, it's a thermodynamic potential used to model the relative stability of different phases, of different densities, particularly. So this is a microstate probability in the grand ensemble, but what we're more interested in is a macrostate probability. This is meant to be a capital P. Let's make it a capital P, which you can derive from the fundamental microstate probabilities, but it goes as an exponential instead of this thing. It goes as the availability potential, which is a function of n and t and mu and v, I guess, divided by kt. So we're now, again, we're still doing equilibrium statistical mechanics of an open system like this, but we're now looking at macrostate probabilities labeled principally here by the number of particles. And it's all given in terms of this availability potential. The availability potential is, very simply put, just the difference between F and mu n, which are themselves thermodynamic potentials, the Helmholtz free energy, and the chemical potential times the number of particles. This is perhaps something you've never come across before, but the name availability has been around since the 19th century and is applied to situations of phase change. Okay, that's good. Once again, it's an equilibrium property. What's this how is this relevant to a non-equilibrium phase change? We will come to that. Room 3, what factors control coexistence and metastability?
Chemical potential, pressure, temperature.
Yeah.
And I guess for metastability, sort of the distribution of the kinetic energy in the system. Otherwise, we can't go over the barrier.
Yeah, all those things which are kind of all contained in the dependence of this macrostate probability upon the various quantities such as temperature, chemical potential, and volume. Less so the volume, because one can scale up and down in volume and still the phase change is going to take place principally when the chemical potential is high enough, that will drive the phase transition, or when the temperature is low enough. So looking out of my window once again, because the humidity is high, that means the chemical potential of the gas phase, water vapor phase, is high. So I'm looking out of the misery is caused by the high chemical potential, and it's also rather cold. So the temperature is low enough, it's below the dew point at the given relative humidity, well, at the given chemical potential. So the environmental factors are driving the condensation. Okay, in a more elaborate materials situation, you might have other factors involved, which could be charge, I guess, or pressure. You could expose this to a variety of pressures and induce different phase metastability and stability.
Composition.
Say again?
It's a composition. So if you have two different
absolutely
chemical species,
you can promote the phase change if you have some catalyst, I guess, or some impurity that promotes the phase transition, that stabilizes the condensed phase or the new form. Okay. Well, these are fairly general questions, so I haven't really taken you very far into this. So I'm going to send you out again and ask you to look at the next tranche of questions. And I think I'm going to put them in, I'll broadcast the questions to your rooms. So, by the way, did you get a broadcast message to say that the rooms were closing in 1 minute? Because that's how I'm going to send the questions to you so that you don't have to go back and forth. Okay. So sending you out to your rooms again and I'll send you some questions by broadcast. Hello, Atiba? Can you hear me? All right, I think everyone's back. So I will ask questions again of you. Room 1 first. Maybe somebody who didn't answer the question last time. Can somebody tell me what the virial expansion is?
So the virial expansion basically takes into account interactions between, or it's a way to simplify the problem in calculating the partition function, hence the equation of state for a system with interactions. And if you add successive terms in the expansion, then it sort of improves the approximation, I guess. So if you only have one term, that's equivalent to the ideal gas law. If you have two terms, that's the van der Waals equation of state. Three terms, I don't know what that's called, but so on and so forth, you improve the approximation.
Exactly. Thank you for that. It's what I've just been sketching here, that the partition function for interacting systems is based upon the ideal gas partition function, which we can easily evaluate. But then there are a bunch of terms in the density raised to some power I, multiplying coefficients. I won't even call them B, some kind of coefficients alpha I. And these are all calculable, these coefficients. N is the density, by the way. So more and more dense gases can be described canonically in a canonical ensemble by producing higher and higher terms in this expansion. It's called the virial expansion for reasons that escape me. The word virial goes back a very long time, but it's a density expansion of the partition function, bringing about things like, as you said, the van der Waals equation of state, which looks like this, which is pressure as a function of volume, with this funny loop that indicates the potential for coexistence. So that's what the virial expansion is. And long ago, actually, many, many decades ago, people computed these coefficients by evaluating diagrams, actually, perturbative contributions to this expansion. So that's the virial expansion, and we need it in order to have the potential for describing coexistence, because just on its own, the ideal gas would never condense because it has no interactions. Great. What about room 2? The question is, why does probability evolve? That's a rather vague question, but maybe somebody can rise to what we're getting at in this context from room 2.
As far as I understood, it has something to do with the nucleation events.
Mm-hmm. Indeed. The question, as I said, is a little bit vague, but in this context, probability evolves because we're dealing with a non-equilibrium statistical process, thermodynamic process. We started out with, in the last set of questions, we had a probability Pn for there to be a certain number n of particles specified in the system, and that probability was specified by this availability potential. But this is an equilibrium potential. This is an equilibrium probability. And what one can say, perhaps, is that there is, for a van der Waals gas over here, an equilibrium probability density at a given, at a point of coexistence, perhaps, where we can draw the Maxwell construction. There is a possibility of an equilibrium distribution of probability between two modes of density or number here. But this is a stationary equilibrium probability distribution. In order for there to be a phase change, these probabilities are not appropriate. We have to evolve from an initial probability, for example, of being precisely at this content, this number here, with a density that looks like a delta function, or maybe it's a Kronecker delta, at this value, but it evolves with time. it spreads and it develops. Time evolution of the probabilities are necessary because we're looking at a non-equilibrium process. We're looking at nucleation. So that was the answer. Thanks for that. And room 3 can tell us what the Becker-Doering equations are.
Can we? As I understand it, it's almost like a rate of equation, a rate law you have in chemical kinetics, except it's probabilities instead of concentrations, which I guess are similar. And you basically treat each cluster of a given size. So it's the rate for a given size cluster. They can either gain or lose 1 unit of whatever you're describing it as. It's like a more restricted version of the Minkowski equation, where normally that can have lots of clusters combined together, but this is just, you can add a particle, remove a particle. And then you can use those probabilities to solve for how that distribution changes in time.
Really good, thank you. That's spot on. It's a scheme for evolving these probabilities in a way that will model nucleation. It's simplified. It has to be, because it's a complicated business otherwise. But the simplifications are that the probability of a cluster of size 3, the probability that the system should contain a cluster of size 3, depends upon the current probabilities, or I guess prior probabilities, that there was a cluster of size 2 present in the system. And there are rates of change between the cluster sizes. This is beta 2, this is beta 3. These are coefficients in the Becker-Doering equations, gamma 3 and gamma 4. Beta are growth rates, gamma are decay rates or evaporation rates. And the Becker-Doering equations, if I can squeeze it in somewhere, are that the rates of change of the Pn with respect to time, and these are not equilibrium probabilities, they're not stationary with time, they change with time. And they look like a beta of n minus 1 into p of n minus 1, which is a growth rate from the size below to the size in question, minus the loss from the size in question at this rate, gamma 3 in this case going down the ladder, and the coefficient is multiplied by the probability Pn in this case. And then there's another 2 terms. There's minus beta n Pn plus gamma n plus 1 P n plus 1. 4 terms, 4 processes giving rise to changes in the probability of the size of cluster in question. You're quite right, these look like concentration equations, rate equations in chemistry, but they refer to probability. They are very similar. Probability in a large system equates to concentration, but really they are probabilities. That's the way to regard it. All right, so we have questions here with answers. We build the availability function using a Virial expansion. We will use them, and that's one of the next questions, to establish a connection between the partition function and these coefficients beta and gamma. That's why that's relevant to nucleation. But we're really interested in solving kinetics of probability, dynamics of probability, and understanding how it is that starting with a monomer, there is, by a growth and decay process, going up and down this scheme, you eventually end up with a big, shiny raindrop that falls out of the sky. Right. I'm going to ask you if there are any additional questions before we move on, and I'm going to ask you once again to go to the rooms, but are there burning questions, are there areas of this that you are puzzled by at this time? I'll take that as a no, and I'm going to send you out again. I guess you all received the broadcast questions last time. It was a little slow coming because of some problem, but I'm going to do that again. I'm going to send you out with more questions. Let me just do that. Off you go. Oh. Alexa, do you like statistical mechanics?
Statistical mechanics is what I like best of all.
Quite right. Right, everyone's back, I guess, and we have more questions, and I hope new speakers. So, you know the drill. Somebody from room 1, please, to give me an answer to why impose detailed balance.
I'm not quite sure on what the exact answer is, but this is referring to the coefficients in the probability rates, isn't it? So in order to find the values of the coefficients, then we can consider the situation when the equilibrium, so that the flux are becoming zero, and then you can do all the equations and you can get rid of some of the terms.
Great, yes, you've got what I'm looking for there. Detailed balance in an equilibrium system is the equality in the rate of a transition in one direction with respect to the rate in the opposite direction. So in equilibrium, we have probabilities here with n minus 1 and probabilities of n, and they're equilibrium probabilities. And then we have a beta n minus 1 going from this size to that size, and a gamma of n going in the other direction. Detailed balance is what I've just said. So beta of n minus 1 p equilibrium of n minus 1 is equal to gamma of n into p equilibrium of n. We know this has to hold because it's referring to equilibrium probabilities. And this is the very definition of what equilibrium means, that there is no net flow between different macrostates. Indeed, between microstates also, but in this case, between macrostates. This is useful because the ratio, and again, I'm just repeating what you just said, the ratio of these coefficients of up and down rates is a ratio of equilibrium probabilities in the grand canonical ensemble, which refers then to a difference in availabilities. Let's get the signs right here. Let's put a negative sign in front of this. This is A of n minus A of n minus 1 over kt. So we know something about these rates. They were introduced by Becker and Düring as just rate coefficients out of nowhere, but they are related to thermodynamics and indeed to this availability potential. And this is the answer to my earlier point. What can equilibrium thermodynamics tell us about a non-equilibrium process? It can tell us the ratio of these rates in a stationary situation. We can use those rates in a non-stationary situation when, as I've already discussed, when we start out with probability at, say, monomer sizes, this is n, this is probability of n, we start out with a probability at monomers only, and it evolves until we have some distribution at larger sizes. A nucleation event has happened. And we can use these rates in the Becker-Düring equation to evolve probabilities. And we know something about the ratio of these rates from equilibrium statistical mechanics. That's why we are bothering with this availability potential and these equilibrium rates. Okay, so that's the question and that's the answer. Why impose detailed balance? All right, room 2. What controls the critical size and the barrier height? Well, what are those things? Somebody from room 2 can tell us.
Could it be so the rate at which this probability can pass across like the central region in phase space? So between the what's it called, the initial state and the relaxed state.
Yes, that's indeed the picture we're building here. We started out at monomers. We put all our probability in that basket, and we wait. Under the Becker-Düring kinetics, we wait. And what happens is that this ladder of cluster size is being climbed and descended from in a repeated fashion like this. This is time evolving as my pen goes up and down. The cluster is growing and it is decaying. And this defines what nucleation means. It means that one is waiting for an incubation period to reach a certain size, which is called the critical size. And once you reach that certain size, which might be, shall we say, here, then whoosh, it's all downhill. And literally so. So the probability doesn't move, but then it moves rapidly across the barrier. There is a barrier at the critical size. And that's what nucleation is. It is the incubated stochastic crossing of a critical zone in macrostate space at a rate which is to be determined. But it is a rapidly changed state that you get a condensation in the example of my raindrops out there. So critical size and critical barrier. Well, what barrier might this be? Actually, I'm going to move on to room 3 to tell us something about classical nucleation theory, what they understand by the classical nucleation theory, and tell us something about the barrier that I've just said is associated with this critical size in the size along the size axis. So room 3, can you tell us something about classical nucleation theory?
Does anyone else want to have a go? Daria? Or, I guess if you have a sphere of some substance that doesn't like forming an interface with its surrounding medium, you'll have a surface tension, and that will negatively, it will create a positive free energy when you create that interface. So there's this favorable contribution for making the thing bigger, proportional to the surface area of, say, the spherical particle you're forming. But then there's also a favorable interaction for actually forming this cluster between particles within it, and that'll be proportional to the volume you have. And in classical nucleation theory, you take that as a constant. As I understand, that free energy is a constant as you just build up, and it's just proportional to the density. But because these are opposite terms with different scaling, so one's an r squared and one's an r cubed, and one's negative and one's positive, you'll end up having a maximum in this. I think that might be my dog's trying to scratch on the door. You have a maximum in this, the free energy change of forming a cluster. So, and where this maximum is, and will give you the critical radius, and the height of this maximum is the energy barrier that you have to go over to be able to form your cluster.
Right, that's exactly right. You've illustrated this picture here, and I've attached to the picture what you've also told us mathematically, that this availability difference with respect to this is defined to be the availability of cluster N minus the availability of the monomer. That's what this delta A is. And when you construct this as a function of N, you find that there is a rising region and a falling region. And in classical nucleation theory, we ascribe the contribution that is positive to a surface free energy. Don't forget that the availability is a free energy minus a chemical potential term. And we have here the surface free energy term, which rises as the surface area, which goes as n to the 2/3. And then there is a payback. There is a negative term, which goes as the volume, as you said, which here I've written as n. And the coefficient in front, delta mu, is the chemical potential minus the coexistence chemical potential at which there is no nucleation, there is actually coexistence, the equilibrium situation between the two phases. So classical nucleation theory takes this picture of a barrier in potential, in thermodynamic potential, with a critical size where the peak is, and where there is a height, A of n, or delta A of n star. And you can work out the height of that barrier by analyzing this form. And in the end, the question, the previous question was what controls the critical size? Well, things like the surface tension and the elevation in chemical potential over coexistence, they control the critical size, whether it's 10 molecules or 1 million molecules in the critical size. They're controlled by these physical parameters of the new and old media phases. Right, so that is classical nucleation theory. In the notes, one can specify that the critical size has a certain form, which I can't remember, but it's something like, no, I can't remember, it's in the notes. There's one more thing to say about classical nucleation theory, which is that the rate of formation of droplets from the gas outside my window goes as something like an exponential of this barrier height. I'll put a delta in front of it. The barrier height evaluated at the critical size divided by KT. And that's a nice picture to go away with, because it's nothing more than an activated process. And we're familiar with this kind of rate expression in all sorts of areas of chemistry, where the rate of a forward reaction goes as some free energy change, some exponentiated free energy change. That's very traditionally taught in chemical reaction kinetics. Here, it's not a chemical process, it's a physical process. It's the rate of formation of little droplets raining down from the sky outside my window. So this is classical nucleation theory. Thank you. That's covered all my questions. There was question 10, which we don't have time for, about second order phase transitions. I'm not sure what else I wish to tell you, except that this classical nucleation theory has been around since the 1930s, and it's based upon very primitive ideas as to what the free energy cost in forming a new cluster is. I think, was it Adrian who told us that the surface free energy is included, imagining that the cluster is a tiny, shiny droplet with a well-defined area. That's not really what these clusters look like. They're completely cluster-like, they're molecular. But nevertheless, what could they do in the 1930s? They could imagine models and run with them. These days, we try to compute partition functions, and hence effective surface free energies. And we use those calculations rather than these primitive models to compute this rate of nucleation. I have finished what I wanted to say, which is kind of good because we've just gone over the hour. I wonder if you have any questions, further questions. I'm going to take that as a no. Time for a cup of tea in a moment. Well, I hope you've got something.
Sorry, John and I were talking. I don't know what the question is fully, but how does the grand canonical ensemble come into this phase, this nucleation phase transition? Because the chemical potentials aren't the same between these two phases. So does it come into it, say, when you're simulating it, or I don't really know?
they are indeed, okay, the new phase and the old phase most definitely have different chemical potentials when nucleation is taking place. And indeed, it's kind of within the rate equation, within the rate expression, there is a delta mu, which signifies the chemical potential of the old phase, the gas, with respect or relative to the chemical potential of coexistence with the liquid. So for sure, the gas is not at the same chemical potential as the produced liquid. The liquid is being produced, I guess, at a coexistence chemical potential because it's just liquid. But the gas was supersaturated. It was metastable and had a higher chemical potential. I think that's at the core of your question. How is it then that we can use equilibrium statistical mechanics, where the two phases are have the same chemical potential? How do we then build this model? The answer is we build the non-equilibrium kinetics by extending somehow, by extrapolating the kinetics of equilibrium. Equilibrium where the up and down rates are equal. We essentially, I haven't said this explicitly, we essentially say, let us imagine when out of equilibrium that all the evaporation rates are the same, but the growth rates are made bigger by virtue of the gas being supersaturated, being overpressurized. And then we use those rates, we extrapolate from detailed balance conditions to out of balance by a bold step of saying all the growth rates increase in proportion to the relative humidity. So if it's 200% humid outside, then all the growth rates are double what they would be in coexistence. So that's the answer. We have a statistical model for equilibrium conditions, and then we boldly go further and extrapolate away from equilibrium. And this is what we come out with. We have Becker-Doering with elevated non-equilibrium growth rates. We'll solve them.
Okay.
Good question. These are subtle things which are often not dwelt upon, but we have at our disposal an elaborate model of equilibrium statistical mechanics, and we extend it as far as we can and see if it works. Are there any other questions before we break, before we go?
No, that's all. Thank you.
That's great.
Thank you.
Well, I'm going to ask a question of Alexa because she helped me in my lectures, as you might remember. So let's see what she thinks. Alexa, do you like statistical mechanics? She's not going to answer now. Alexa, do you like statistical mechanics?
I don't have an opinion.
Well, I programmed you to have an opinion, so she's being most uncooperative. Shall we try once again? Alexa, do you like statistical mechanics?
Statistical mechanics is what I like best of all.
There. I've got an appreciative audience in the room here. Okay, I've said enough. Thank you for your attendance here. If you're interested in the topic, there's plenty of material for you to read about in my notes, further than I could possibly discuss in lectures. All right, have a good day, everyone. I'll close.
Bye.
Bye-bye. Thank you.
Thank you very much.
Bye-bye.
Thanks. Bye-bye.
Thank you.
Thank you.
Thank you. Bye.